Hello, and welcome to Aggressive Physics. Today is day 45, and we're going to begin our discussion of friction. Now, friction is a force that opposes motion. So we have different types of friction that exist, but we're going to generically define friction as any force that opposes motion. We can have air friction. We could have friction between surfaces. We could have friction of the water pushing against a boat. We can have rolling friction. There's many different types of friction, but for our purposes, we're going to just define friction as a generic thing, and any force that goes backwards when an object moves forwards, any force that goes down when an object moves up, or in the other case, if an object's falling, any upward force would be considered friction. Now, friction has a byproduct when it's sliding against something, which is going to be the main friction we discuss in this course, because we're going to be able to calculate it. And the byproduct is heat. When you take two objects and you rub them together, we have friction, like when I'm rubbing my hands together like this, and the friction is causing heat. That friction is caused by the rubbing of the surfaces together. So what we effectively have is a situation where two surfaces are rubbing against each other, and microscopically they're rubbing against each other at different points of contact. Now, any object microscopically has bumps and grooves on it. So if we were to look at something under a microscope, we would see that even an object that appears smooth is actually extremely bumpy. And as it moves across another surface, that surface is also going to be bumpy. And we can see rough surfaces like a piece of wood that hasn't been sanded. That's obviously has a lot of bumps and grooves. But even surfaces like a classroom desk or a kitchen table or even a floor like a tiled floor or perhaps a hardwood floor, that even in those cases microscopically will have a lot of bumps and grooves. So as the object slides over the other surface, you're going to see that those bumps and grooves are going to come into contact and they're going to rub against one another. That will cause a backward force on the object that's sliding and eventually causes it to stop moving. In space, we have much less friction due to wind resistance, and there's no surface involved if we're in deep space and we're just pushing a pen again, let's say. So what would happen is you'd have very minimal friction. We have often in laboratory settings air carts where we have a situation where air is pushed through a track, very similar to an air hockey table, and that will limit the amount of contact between the surfaces. So in order to undermine friction, if you will, we have a number of things we can do. We can change the surface contact itself. Going back to the piece of wood example, we could sand the wood and make it smoother. We could coat the wood with polyurethane or even a stain, and what that will do is fill in some of the bumps and grooves and actually allow other surfaces to slide on it more easily. If you take polish and put it on a dining room table and then try to slide a plate across the table, you're going to see that the friction is decreased significantly. Please don't do that at home. I don't want you to break your family's best china. But just for the example, when you put the polish on it, it's filling in the bumps and grooves of the table itself. And then when a plate is trying to move across the table, you're going to see that the amount of friction is decreased significantly. Now, friction isn't always a bad thing. We think of friction as a negative. But friction is the reason we're able to walk. Friction is the reason that cars are able to move forward. The tires in the ground need to have friction in order for the tire to roll. We often call that traction, though, when we're dealing with friction as a positive in that case. But friction is necessary for us to move at all. If we were to stand on a frozen lake and it had completely smooth ice and we tried to walk, our feet would just slide backwards and there'd be nowhere for us to move. We'd actually probably need to use Newton's third law. Take a heavy object like a rock and throw it in one direction, and then we can slide backwards across the ice. That would utilize Newton's third law and the fact that we would then have inertia to keep moving, and without any friction, we'd be able to slide across on the ice and reach the other side. Now, we do have an equation in order to calculate friction. And that equation is simply friction equals mu Fn. Now, we often denote forces with an F and then a subscript to denote the type of force we have. We've done F sub g for gravity. Ultimately, we're going to do Fe for electrostatic. We could do Fm for magnetic. We could do forces for just about any different thing. In fact, we even have F sub n for normal. And in this equation, that F sub n is the normal force. Now, there's two terms in this equation that are new to us: friction and the mu. Now, friction is just the force that we're going to calculate. It's no different than F equals ma. But when I deal with friction, I like to denote it as something different than just a regular capital F sub F. So I'm going to use a little curvy F, if you will, almost like a script F to denote friction. And that way, in my mind, I know that friction is going to be backwards from the motion. And when I set up my equation, F equals ma, and I do the sum of that F equals ma, I'm going to know that that frictional force is going to be negative. On my free body diagram, I'm going to draw it opposite the direction of motion. So anytime the word friction comes up in a problem, you're going to want to draw it backwards from the direction of motion. So if an object is moving down an inclined plane, friction would go up the inclined plane. If the object is moving up the inclined plane, friction will go backwards down the inclined plane in the negative F parallel direction. Now in that case, if an object's moving up the hill, what will happen is F parallel, the part of gravity pointing down the hill, and friction would combine to slow the object down. So you wouldn't just have the frictional force opposing the motion, you would also have the parallel force opposing it as well. So the parallel force would be added to the frictional force, and that would contribute to the negative term of that motion. Often we'd just have an object, let's say, slide up a hill, and we'd want to find out how high it would move up the hill. Well, in that case, the only two forces acting on it would be F parallel and friction, and they would oppose the motion. Now, since we'd often have initial velocity in that case, we would have to find the acceleration due to those forces and then calculate the A from that, and then use that A in one of the old kinematics equations, one of the big five, in order to calculate, for example, D, the displacement up the incline. So friction is just another force, but we have a way to calculate it using this mu Fn. Now the other term is this mu. Now we may remember mu as a prefix when we talked about the metric system. And mu represented 10 to the negative 6, or micro. Now in this case, it does not. So it all depends upon the context by which the mu brings itself into the problem. In this case, mu represents what we call the coefficient of friction. It's a measure of how much friction is available between two surfaces. The lower the coefficient, the lower the total amount of friction. Now the value for mu ranges between 0 and 1. And since it's a coefficient, it doesn't have a unit at all. It's just a multiplier, if you will. So what we have available to us is a chart of coefficients of friction. And that chart is located in the reference table. Now, if you look at that chart, you'll see that there are two columns on the chart. There's a column for static friction and kinetic friction. And what we're going to talk about a little later is the difference between the two. But for right now, if we look at the chart, we'll see values that relate different surface combinations. And on our chart, we use combinations that would be common to a physics problem. For example, we have rubber on concrete when the concrete is dry or wet. We have rubber on asphalt when it's dry and wet. And those are so that we can do problems where a car is traveling on concrete, maybe a driveway, or it's traveling on asphalt on a road. We could have coefficients between other surfaces that cars could travel on, maybe packed dirt or gravel. But for our purposes, concrete and asphalt will typically be the problems that we try to solve. Other combinations involve rubber on ice and wax skis on snow. So if you're trying to drive a car on ice, you could have certain values for coefficients of friction. And then if you're trying to use wax skis on snow, we'll be able to do problems dealing with skis and someone skiing. You could do the same thing with a snowboard. And what we'll typically do is use snowboards and skis as similar surfaces. Now, of course, they're going to be slightly different. But since we don't have a value for snowboards, if we do a snowboard problem, we'll probably use the same values for wax skis on snow. Now, other types of combinations are wood on wood, steel on steel, copper on steel. What we'll use for those are typically, if we're in a laboratory setting, we may have different metallic masses made of different things, like a copper mass versus a steel mass versus maybe even a wooden block, and we'll slide those on different surface combinations. Maybe the lab bench will have a piece of metal on it, or we'll have a piece of wood, and we'll be able to figure out the coefficient of friction from that, or find the amount of friction involved. Finally, we have Teflon on Teflon, and that's when you have typically the no-stick surface for frying pans involves Teflon. That type of surface has a low coefficient of friction, so that's why they consider it a no-stick surface when you're cooking. Now, the no-stick surface can be rubbed off. It's basically just a spray on top of the pan itself. So over time, as you're cooking, if you use metal spatulas, that'll rub away that Teflon coating. That would increase the amount of friction, and it will not have that no-stick capability anymore. So I think most of the manufacturers suggest that you use plastic spatulas, and I'm sure ones that they sell specifically for their frying pans, but that will limit the amount of the Teflon being rubbed away. Every time the Teflon is rubbed away from the surface of the frying pan, that's going into the food, and you're actually eating some of that no-stick surface. Not to alarm you, it's probably low amounts, but it's still something that can happen and will happen over time. Now, the values for some of these, for example, we have 0.68, 0.58, we have 0.67, 0.53, and we have all the way down to 0.04. The larger value for the coefficient of friction, the bigger the amount of friction that can exist. Now, finally, the normal force is going to be involved. And the normal force is between the surface and the object that's on the surface itself. And remember, because of Newton's third law, that force is common between the two. So we have the amount of surface contact dependent on the amount of friction as well. So what can happen is you can increase or decrease that surface, the amount of friction, by changing the normal force. For example, if you're trying to push a heavy dresser across a carpeted floor, you're going to find it difficult to do with all the clothes in the dresser. So what you can do is take out the drawers themselves. That will decrease the overall normal force, and that will decrease the overall friction. If you're trying to push a car and the wheels are locked, it's going to be very difficult. But if you decrease the normal force by having the passengers come out of the car, it's going to make it easier. There'll be less friction on the vehicle itself. Now, that being said, we have different situations where we can try to find the total friction. The bigger the normal force, the bigger the friction can be. The bigger the coefficient of friction, the bigger the total amount of friction can be as well. Now, that is a difficult concept for students to grasp in the fact that the coefficient is not the amount of friction. The coefficient times the normal force gives you the total friction. Now, the coefficient of friction cannot be changed between two surfaces in a problem. The only way you can do that is by actually changing the surface combination itself. For example, if we have wax skis on snow and all of a sudden we don't have wax on the skis, that would be a way to change the coefficient. We're not going to change the coefficient by adding mass or decreasing mass. That would change the total friction itself. Now, the way we're going to calculate friction, since normal force has a value of newtons and coefficient has no units at all, the frictional value will be in newtons as well. So friction is just going to be another force, and it's going to be measured in newtons. Now, what we can do is calculate a number of different values for friction. Perhaps we'll have friction in a laboratory setting. You may drag a block across a table and use a spring scale to figure out the value of the force. Now, a spring scale is just a scale that's calibrated with a spring, and it has a different setting on it, probably newtons. And as you slide it, you're going to get a value for the amount of force involved. If you held it vertically, it would tell you the force of gravity on the object. If you slide it horizontally, it would be the force that you're applying to the object. Now, if you're able to slide it at a constant value, your force would be equal to friction, because at a constant velocity, there's no acceleration. And if you had your force minus friction equals ma, and the actual acceleration was 0, well, that would mean the force that's reading on the scale would be equal to friction. Well, if you knew the normal force, and you could do that by now holding the block vertically and measuring that value, and as long as you're holding everything horizontally, gravity is going to be equal to the normal force in this case. Well, you should be able to figure out the coefficient of friction by doing the division between the value on the scale and the value of the normal force. And you could find, the coefficient of friction in a laboratory setting. In my classes, we're going to do that as one of the labs, but for everyday, experiences, you could just do that at home. You could slide an object with a spring scale on a carpeted surface, write that value down, figure out the normal force from just using the scale vertically, and it was going to be equal to the gravitational pull, and dividing the two. And what you can do is find the coefficient of friction between any two surface combinations. You could do a carpeted surface and a textbook. You could do a carpeted surface and a plate, or any object that will slide. Now you could take that object and slide it on a hardwood floor or a tile and see how the total friction changes, and ultimately how the coefficient of friction changes as well. So coefficient of friction is going to be a term that is dependent upon the surfaces. It's not going to change in the problem. It could change if you all of a sudden put an oil slick down on the ground, or you sand a wooden block or something like that. But for our purposes, within a certain problem, the coefficient should remain constant, and the total friction will then be dependent upon the normal force as well. Calculating it is simply finding the coefficient. If you're given a surface combination like wood on wood, you look it up on the chart, you use the kinetic value because it's moving, and you calculate the amount of friction if you know the normal force as well. I typically draw free body diagrams to make sure that all the forces are labeled and to make sure that the normal force is equal to gravity. If we're on an inclined plane, the normal force would typically be equal to the F perpendicular value, and we would find friction based on that value, not all of gravity. If we had objects riding on top of the surface, we have a textbook, and then we put masses on top of the textbook, well, then we'd have the normal force be the combination of the masses on top of the textbook and the textbook's mass, or force of gravity itself. So we would have to find the force normal first, multiply it by the coefficient, and then we can find the total frictional value. What this will do is give problems more leeway. They may give you less numbers, but more words that denote the surfaces themselves, perhaps the normal force, and then you're going to be able to find the friction from that. So we're adding a layer of complexity to problems, but since most objects on the Earth's surface are experiencing friction, it allows us to solve more realistic problems as well. So with complexity also increases our realism, and the problems can be more realistic, more related to everyday life. That being said, what we'll do is a couple of sample problems now dealing with friction, and then we'll add complexity to that and solve more complex problems from there. And that concludes our discussion of friction for today. I thank you. So we talked about the fact that friction has an equation, mu Fn. Now, the Fn we've been discussing already, and that was the normal force. And that had to do with the surfaces. Well, the mu was the coefficient of friction. And that is going to be based on whatever the surfaces involved are. And as I stated before, anytime you have a surface, no matter what, it's going to be microscopically rough like this. The only instance where you'd have a really smooth surface that may not have this kind of microscopic view would be if you're looking at some really polished glass or something like that. Well, in that case, you'll actually be dealing with something other than friction. You'll be dealing with pressure. Because if you have something that's completely smooth and you push them together, you end up creating a little vacuum in between. If it's just air, it'll be difficult to pull apart. So if you had a handle here, you'd try to pull on the handle, up and down, and it'll be difficult to separate. Now, if you were to put oil or water in there, due to the properties of water or oil, because of the cohesion, that is going to cause a vacuum that's even has more strength, and it'll be even harder to pull apart. If you have a set of dishes that are really close to fitting within one another in your cupboard, what you can do is actually put a little water in between it while you're washing them, and then push them together, and then try to separate them with your fingers. It's very difficult to do. Now, like I said, though, most objects do have some rough surfaces. So what we have here is a overly dramatic view of, maybe a book on a table. And of course, the book and table look smooth, but microscopically they're rough. And this obviously is dramatized, but it shows that as they're going to move against one another, they're going to rub and hit the different teeth in this diagram. Now, one way to limit and change the coefficient of friction would be to sand the table. Maybe I sand it down, and now we have much smaller teeth, and there's less spots to get stuck. Or another way we can do that, if we have our original table back, here's our original table, we could take some kind of lubricant, maybe water, and we could fill in the grooves. And as you fill in the grooves, what's going to happen, it's going to allow the book and the table to slide over each other more readily. So in this case, if I fill in all the grooves, I'm going to have less friction. Now that's a case of changing mu, though. Over the problems we're going to have mu's constant. And even one of the things they discuss on the reference table is they have mu's for dry versus wet materials, like concrete or asphalt. So if you're driving in the rain, there's a different coefficient of friction than if you're driving during dry conditions. But either way, the coefficients of friction are based on the surface combination. If I were to take the table out of the equation, and now it is, we'll call it a rug. And we have the same book. And of course, I'm not going to draw the book the same, but this scenario would have a different mu than the book versus table. So this mu is unique for each surface combo. That being said, if I change one of the surfaces, I'll change the mu. And I could change the surfaces physically, take the book and place it on the ground, place it on a rug, or I could physically change the surfaces by sanding it down or changing it in some other way, polishing it or something like that. But our equation for friction is based on two things: the normal force, which is the force between the two objects because of Newton's third law. So this might be the action, and this is the reaction. And then the mu, which is a measure of the potential amount of friction. The higher mu is going to range between 0 and 1. The bigger the number, closer to 1 it is, the more potential friction there is. The smaller, closer to 0 it is, the less the potential friction exists between the two surfaces.